In the lecture, this is lecture 6. This application of the chaos theory on real problem, and in these cases, I would like to show the cases of the citrus alternate bearing. Okay, one of the typical toy model on the chaos is RBM. RBM is abbreviation of the resource budget model. This model is used for the alternate bearing at the tree club. This is citrus unshu, the data. The left hand side of the figure shows the national production of citrus unshu from 1973 to 2016. As you can see, a total amount of the production is declining, and the left-hand side figure shows the difference of the each neighboring years increment of the year. As you can see, very clear on and off differences could be observed. This is called as alternate bearing in market. In the last lecture, we explained the system which generated the synchronization. Oscillators is this time is a citrus unshu. Synchronization is appeared in the as national production fluctuations. This is a slide of the on-year tree and off-year tree in the same year in the same orchard. This is the data obtained from the two experimental trees, and without any thinning, any fertilizing, just obtain the fruits in every year. In the early stages, they show some in-phase synchronization. Afterwards, from the 1965, they started to show the out-of-phase synchronized out-of-phase. This is we already explained it last time, but I repeat it again. And citrus alternate bearing dynamics. This slide shows resource budget models, and we premise the bucket inside the tree, which accumulated the energy in their body. We use IN represented that. LT is threshold. PS is photosynthesized residue in each year. We assume that every year's weather is same. Therefore, the PS is constant. In this year N, there is no overflow here. Therefore, no fruiting. Therefore, the large amount of the energy is accumulated in the bucket. This energy is materials transferred to the next year. In the next years, and the same amount of the photosynthesized residue is added on the bucket, then this green part is used for the cost of flowering. This amount of the RC times CF is the cost of fruiting, and the red part is the fruiting cost. Then large amount of the acorn production there we can see. Therefore, this is in on year. This is of year. This is a simple and dynamics of the resource budget models. Also, expression with a different equation by the graph, and it is a kind of the return plot, in versus in plus 1, and the red part is non-flowering regime, and the blue one is off-year regime. This process is described by the difference equations. In a stock, in plus 1 is, in these cases, there is no overflow. This cases is overflow from the threshold, and the flower is here and fruit is here. Also, expression with a different equation by the graph, and it is a kind of the return plot, in versus in plus 1, and the red part is non-flowering regime, and the blue one is off-year regime. This is a cobweb dynamics of the resource budget model. This is left-hand side is return plot, right-hand side is time series. In the flowers, and CFN and CFN plus 1 is plotted as a return plot. This is equations. Okay, this is a plot, and if you run the program of this, and you can get the you can see the animation on that. Okay, for example, this is the real data obtained in the Nebukawa experiment stations, and from 1970 to 1989, then and 378, that's the same data. Then and to create a return, this is the time series, and from the blue part. Then and this bottom figure is return plot, and x-axis is here, y-axis is here. Then you can see the very clear dynamics like this. The slope of this part is RC. This one is actual data. How we can determine the dynamics only from the time series data? This is one of the typical ways to reconstruct of the dynamics. Return plot is very popular one. We have this is an experimental station in Nebukawa. We have 48 citrus trees measured each tree's yield for 7 years, like this. This is tree number 1, tree number 2, tree number 48, and this number is the number of the fruits, and this histogram is the each year's fruit number histogram. This is just return plot of all the 48 trees for the 7 years measurement, and this shows we cannot see the dynamics here. If we plot the three-dimensionally like this, xk t xt minus 1 t 2, like this. This we have this is a vectors. Then f is a reconstructed dynamics from the ensemble time series. How can we determine the f is the key? This is a way to do one for the predictions. In the to show this concept is I prepare the way of the explanation. This is the tree number 1s. This is tree number 10. This is tree number 19. Tree number 14. Okay, if we wanted to predict the tree number 14's 1 year forward yield predictions, to keep the pattern in the 3 years, bring this pattern back to the compare with the other trees' past patterns. In tree number 2, we cannot see any good pattern. 19. Okay, maybe these 19s past three number 19, the past pattern will be similar to the number 14s. Therefore, to bring this data as back to the number 14, then and this pink value is used as a 1 year forward prediction of the yield of the number 14. This is ensemble reconstruction of the dynamics. Then, using this procedure, that is 1 year forward prediction of independent yield. Therefore, most of they showed very good fitting. Only 1, 2, 3, 4, 5, 6, 7, 8. Okay, this arrow shows cases which failed the predictions, but only 8 cases failed among 144. Therefore, the 95% of the prediction was possible. Okay, this blue is the histogram of the actual yield, but the red part is a predicted histogram. Therefore, in terms of the histogram, this prediction, 1 year forward prediction, would be successful. This shows the predict actual plot. This is left hand side is in terms of the yield. Right hand side is increment. To see the increment, it is very clear, very high accuracy we can obtain in the predicted actual plot. Why the two features are important for us? If we could determine the dynamics behind the random looking fluctuation, we can use the dynamics as a model of the phenomena. The model can be used to predict and developing a control logic for the phenomena. And this is one of the typical output as evidence of the deterministic chaos. Then, once we obtain the dynamics, we can use this dynamics to develop the algorithm to control the system. And without any control logic, they starting from this initial value, the system shows an on-off periodic cycle, limit cycle. Then we calculate the control input UT. UT is calculated as a equation of the OGY control method. This is a number of the thinning fruits. Then in this period, and the control is controlled input is available. Therefore, the state is control on the fixed point. Fixed point is stable fixed point. With using the control input, we can maintain the state in here. However, with the time evolution and the small differences in the exponentially increase, then it came back to the period limit cycle. And this is a quite idealistic case. There is no environmental noises. And usually we have environmental noises, and in that cases, and period without a figure A as a time series without any control, it shows a fluctuation of the on-off fluctuation with noise imposed. In the controlled, in here bottom figure C shows unstable UT is here. It's to maintain the state in the fixed unstable fixed point. We have to continue to input the control UT. Then once the control was finished, it's easily come back to the periodic cycle. This is this control model is corresponding to the conventional sinning technique. Okay, well, I also explain this. Synchronization consists of non-oscillators.